In this video, we will explore one of the most iconic and still unsolved problems in classical geometry, the quadrature of the circle. For centuries, mathematicians have searched for a way to construct, using only a compass and straightedge, a square with the same area as a given circle. But what if the problem was never about tools, but about the assumptions behind them? This is not a historical reenactment. What you're about to see is a completely new geometric approach, one that unveils deep, hidden relationships between circles and squares. We'll go beyond simple area equivalence. Step by step, we'll uncover golden ratios, fractal square growth, and mysterious intersection points that hint at a deeper structure of space itself. And we won't stop there. We'll take this concept further, into territory that classical mathematics has barely explored, and show a constructive quadrature of the ellipse. This opens the door to new insights into form, proportion, and the geometry of nature. If you believe that the language of the universe is written in shape and ratio, then this video will give you a whole new way to read it. Let's now take a closer look at this construction, uncovering what lies beneath the surface of this ancient geometric challenge, and seeing, step by step, how the square and the circle begin to speak the same geometric language. Before I begin with the actual demonstration and explanation of the geometric constructions, I would first like to highlight one important detail regarding units of measurement. In this research, I will be using millimeters, with 1 millimeter representing the basic measurement unit. However, this does not mean the method is limited to millimeters. It is based on a universal proportion, which means that any other unit, centimeter, meter, inch, and so on, can be substituted with the same value, and the results will remain completely identical. In my previous video titled Phi Code, I presented in detail the system of fractal division of the circle and, based on it, developed new formulas for calculating perimeters, areas, and even volumes, all in accordance with the golden ratio. I will not go into those topics in depth in this video, but I highly recommend watching that presentation for a better overall understanding. Nevertheless, I am once again showing those key formulas here, as they will help us later in understanding the constructions and verifying their correctness. We will start with a basic circle with a radius of 1 millimeter, meaning its area, according to the classical formula, is equal to pi square millimeters. If we construct its golden circle, the one that follows a geometric sequence, we get a new circle with an area of 1.2 square millimeters. That is a purely rational value, surprisingly elegant in its simplicity. This confirms the first group of formulas, where the area of the golden circle is no longer tied to the transcendental number pi, but instead to an expression that includes the square root of 5 plus 3. Now, if we inscribe another golden circle within this first golden circle, a fractal continuation based on the same principle, we no longer get a rational area, but instead we obtain a rational circumference. In this case, exactly 2.4 millimeters, which we can again confirm using geometric formulas. This gives us an interesting twist. The first golden circle yields a rational area, and the second one a rational circumference. When we analyze this in the context of the golden spiral, we discover extremely interesting proportions. On the right side, we can see a spiral, where the smallest arc measures 0.6 millimeters, which is exactly 3/5 of the base radius. This length is then multiplied twice in succession by the golden ratio, first reaching 0.97082 millimeters, and then 1.57082 millimeters. And what is crucial here, this sequential fractal growth clearly reflects the kind of natural growth we see in seashell spirals, in the arrangement of leaves, or in the proportions between parts of the human body. This is a simple yet powerful demonstration that pure geometric constructions can yield results that transcend the classical limits between rational and irrational, revealing an underlying order that could rightly be called a natural code embedded within geometry itself. The same natural growth we just observed within the golden spiral is not limited to circles. It can also be clearly seen in square fractal growth. It is this square-based growth that opens up a completely new possibility, the geometric quadrature of the circle, meaning that we can, through simple and precise constructions, create a square with the same area as a given circle. This problem, known as squaring the circle, was for thousands of years considered one of the most legendary mathematical challenges. In classical mathematics, it was declared impossible, because supposedly it is not possible to construct a square with the same area as a circle using only a compass and a straightedge, primarily due to the irrational nature of the number pi. However, within this new geometric paradigm, based on fractal growth and the golden ratio, it turns out that squaring the circle is entirely possible, if we redefine the starting conditions and use the natural units already inherent in the circle itself. Let us begin with a base circle that has a radius of 1 millimeter. According to the classical definition, its area is pi square millimeters. Now, if we look at how the square construction begins, we start with 3/5 of the base radius, which equals 0.6 millimeters, the exact same value we previously encountered in the spiral. From this length, we construct the first square. This square is then scaled up using the golden ratio. We find its midpoint, transfer the diagonal to the base, and in this way obtain the second length, 0.97082 millimeters, which we then use to construct the second square. We repeat the process. Find the midpoint of this new length, transfer the diagonal again to the base, and obtain the third length, which is 1.57082 millimeters, and from this we construct the third square. Now we have in front of us a sequence of squares that do not grow linearly, but fractally and exponentially, and at the same time in harmony with circular growth. Once we have built this sequence of 3 consecutive squares, the third square allows us to construct a square with the same area as the original circle, and this can even be done in 2 different ways. The first method of construction goes like this. If we draw a parallel line from the midpoint of one side of the third square towards the edge of the neighboring circle in the chain, this parallel intersects the circle at a point from which we can geometrically derive half of the diagonal of the square with the same area as the circle. If we then rotate this length by 90 degrees, we can use it to construct the full square. In this case, the square is concentric with the circle, creating a clean, balanced structure. The second method of construction starts from the point where the side of the third square intersects the edge of the neighboring circle in the chain. In this case, we do not obtain the half of the diagonal, but the exact length of the side of the square with the same area as the circle. So, from the center of the third square's side, we can construct half of the diagonal. From the actual right side of the square, we can construct the exact side length of the square. This clearly shows a dual construction process, 2 different approaches that lead to the same result, further confirming the deeper logic and consistency of this system. Now, if we take a closer look at the left square, the one that is concentric with its circle, we observe another fascinating geometric phenomenon. In several places, the square and the circle intersect. These intersection points allow the construction of an inscribed square within the base circle. Its side measures the square root of 2, which is not a coincidence, but an additional proof that this construction is based on harmonic and geometrically well-aligned proportions. This is not merely a visual curiosity. It is a complete system that reveals the inner geometry of natural proportions without any need for the traditional number pi. The golden ratio, the square root of 2, and the logic of dual construction all work in harmony here, and this is precisely what opens the door to a new field of understanding the quadrature of the circle. If we were to construct, using this method, a square from the first golden circle, the one whose area is exactly 1.2 square millimeters, such a square would, by its very geometry, confirm the accuracy of that value. In my previous video, which I already mentioned, I demonstrated a progression of circles using only whole numbers without the value of pi entirely through construction. And once again, for each of those circles, it is possible to construct its corresponding square, thus confirming the validity of this method, since the results always yield a perfectly accurate whole number outcome. Squaring the circle is therefore neither an illusion nor an impossible task. We were simply looking at it from the wrong direction. When we allow nature itself to guide the structure through fractal spirals and square golden growth, all elements assemble themselves into perfect order. The circle and the square, 2 ancient symbols of perfection, unite in a new geometry where there are no longer barriers between the rational and the irrational, between the line and the curve. There is only growth, and from that growth arises the truth of space. We will now apply the same method to the realm of ellipses and demonstrate how, using a fractal construction technique, we can build a rectangle with the same area as a given ellipse. To illustrate this procedure, I have chosen an arbitrary ellipse with one semi-axis measuring 1 mm and the other 2 mm. Once again, we make use of a so-called neighboring ellipse, much like we did earlier with squares and circles. We begin by taking the longer semi-axis of the ellipse and dividing it into 5 equal parts. From these, we select 3 parts, meaning we begin with a length equal to 3/5 of the longer semi-axis, or 1.2 mm. This length defines the side of the first square. Following the previously established method, we enlarge this square using the golden ratio until we reach the third square. This third square intersects the ellipse at a point which serves as the geometric reference for area equivalence, the point from which we can construct a rectangle with the same surface area as the ellipse. From this intersection point, we construct the first segment, which becomes the longer side of the rectangle with the same area as the ellipse. Next, we draw a parallel line through this segment, originating from the circumscribed rectangle of the neighboring ellipse. This part of the construction serves as a guiding grid for the continuation of the method. Finally, from both endpoints of this segment, we draw perpendicular lines up to the parallel line, thereby defining the second side of the rectangle. In this way, through geometric logic and without the use of the number pi, we have constructed a rectangle with the same area as the chosen ellipse. For calculating the area of the ellipse, I have derived an alternative formula, which is presented here. When we insert the semi-axis values, the result perfectly matches the area of the rectangle obtained through geometric construction. This match between the numerical formula and the construction result is not a method of conversion, but rather an independent confirmation of the validity of the entire method, just as we did with the circle. Geometry and arithmetic here work hand in hand. The formula does not replace the construction, it confirms it. This method therefore offers not only a compelling visual result, but also reveals a profound harmony between rectangular and elliptical surfaces, where the entire construction is rooted in the inner harmony of geometry itself. In the end, what we've explored is more than just a new method of geometric construction. It's a different way of perceiving space. By stepping beyond the traditional boundaries of mathematical constants and allowing form to grow naturally from within, we open the door to a deeper understanding of proportion, structure, and truth. The golden ratio becomes not only a number, but a guide, a compass pointing toward the underlying order that geometry has always sought to express. If you find value in this work and wish to support its continuation, you'll find all the details for contributions and donations in the description below. Your support, whether through a donation or simply by sharing this video with others, helps bring this exploration to a wider audience. Thank you for watching.